So in the previous lectures, we were discussing about the token bucket regulators or the rho sigma characterization of the traffic source. So we will continue the traffic characterization of a traffic source by the rho sigma parameters, and we will see some of the properties of such linearly bounded arrival processes. Just to recapitulate what we have discussed in the previous lecture is that what we are saying is that we will represent a traffic source by a linearly bounded arrival process or by deterministic traffic descriptors, which is sigma and rho, and these sigma and rho parameters are such that a number of bits transmitted by a source during any interval of time t is bounded by sigma plus rho t. So therefore rho admits the interpretation of an average rate and sigma admits the interpretation of some sort of burst that a source can transmit. We also saw that such a linearly bounded arrival process can be generated by a token bucket regulator which has a maximum bucket depth of sigma and which has the token generation rate of rho, and whenever a packet comes, the bucket is decremented by the length of the packet, and if a packet comes and if it finds that there are not enough tokens available in the packet, then the packet is queued at the packet buffer at the traffic source site or at the traffic regulators. We also saw that among all the Fifo controllers that will generate the rho sigma traffic, a token bucket regulator delays the traffic the least among all these Fifo controllers, and therefore the token bucket regulator is some kind of an optimal traffic regulator for a rho sigma traffic characterizations. So now we will continue this discussion further of the rho sigma traffic characterizations and study some of the properties of these rho sigma regulated traffics. Okay, so let us start with first the effect of multiplexing. Okay, so multiplexing of several rho sigma traffic. So what we are saying that, and this is an ideal multiplexers. Okay, so we call it to be an ideal multiplexer. The input traffics are represented by A1t, A2t, so on till ANT, and the output is AT. Now this is an ideal multiplexer, so therefore the output AT is given by A1t plus A2t plus so on ANT. Now here AIT is denotes the number of bits transmitted or the number of arrivals transmitted by the traffic source during the interval of 0 to t, or in other words we can say that these are the number of bits or cumulative number of arrivals by the time t. Okay, so this also represents the AIT also represents the cumulative number of arrivals of a traffic source I. Now an ideal multiplexer, we want to characterize an ideal multiplexer when the input to such multiplexers are rho sigma regulated. An ideal multiplexer gives an output which is the sum of all these traffic sources. Okay, so our claim is, so we say our claim is that if all these AITs are rho sigma constraint, that is sigma I rho I constraint, then the output A is also sigma row constraint, where what is sigma? Sigma is the summation of all sigma i's, and what is row? Row is the summation of all row i's. So we will try to prove this. What we are saying is that suppose if we take an ideal multiplexer, the input to such ideal multiplexers are row sigma constrained traffic. We are trying to prove that the output will also be a row sigma constrained traffic, where the sigma will be the sum of the sigmas of all the input traffics and rho will be the sum of the rows of all the traffic. So let us try to prove this a proposition, and then we will see a practical example of that. So the proof of this is, note that the traffic I is row sigma regulated, therefore AIT minus AIS. Now AIT is the number of arrivals by the time t and AIS is the number of arrivals by the time s. Therefore AIT minus AIS is the number of arrivals or the number of bits transmitted during the interval of t to s. Now since this traffic is row sigma regulated, this will be less than or equal to sigma I plus rho I into t minus s, right. Now, so this is the interval. Note in our previous discussion we were using the t for the interval, for the time interval. Here now we are using the variable t to denote a time instant, s is another time instant, alright. So AIS is the number of bits that have occurred by the time s, AIT is the number of bits that have occurred by the time t. So AIT minus AIS is the number of bits that have occurred during an interval of now t minus s, t minus s is the interval. Now since this traffic is row sigma regulated, therefore these number of bits which have been transmitted during the interval of t minus s, that is from the time instant s to time instant t, okay, will be less than or equal to sigma plus rho into t minus s. And now this is valid for all i's, alright. So I will say that this will be valid for all i's from 1 to n. Now we sum up all such inequalities, okay. So if we summing up all such inequalities for I equal to 1 to n, then we get AT minus AS, okay, that is the number of bits which are transmitted during an interval of t to s at the output of the multiplexer will be less than or equal to summation of sigma I for I is equal to 1 to n plus summation of I is equal to 1 to n rho I t minus s, and hence we have proved that the multiplexer output is a row sigma regulated traffic, where the sigma is the sum of all sigmas and rho is the sum of all rows. Now it can be seen sometimes that this multiplexer can reduce the burstiness, okay. Let me just give you an example of this multiplexer. Now we have this multiplexer which is an ideal multiplexer. Let us say it has two inputs, A1 and A2, and this is the output, right. Let us say A1 is 1 0 1 0 1 0 like this, okay. So these are the number of arrivals that are occurring at these time instants, okay. So this is how the traffic A1 is, the number of packets or number of bits which are generated. A2 is 0 1 0 1 0 1 so on. Now if it is an ideal multiplexer, So output A will be the sum of these two, and we get 1 1 1 1 so on. Okay. Now what is the input A1? If you look at this input A1, okay, it is the input A1 is actually one into half constraint traffic, right? Sigma here is 1, right, because we can maximum burst here is of 1 unit. Okay. So because the traffic is transmitting as 1 0 1 so on. Okay. Similarly A2 is 0 1 0 1, so it is also 1 and half constraint. Okay. So that is the average rate is of half. So this is also 1 into half constraint. But if you see this input traffic, which is the output 1 1 1, so how it is constrained, 1 1 1, output is actually is 0 1 constraint, right. So the output, if you see, is zero one constraint. Now if you had applied this theorem, the previous theorem, then the output should have been sum of sigma i's, which would have been 2, okay, and sum of rho i's, which would have been 1. So output should have been 2 1 constraint according to this theorem. According to the theorem, output should have been, according to our claim, output A should have been 2 1 constraint. So indeed what we see that this theorem, which says that the output of an ideal multiplexer, which will be the ideal multiplexer where the inputs are all sigma rho constraint, the output will also be sigma rho constraint where the sigma will be the sum of all the sigmas and rho will be the sum of all the rhos. This result in fact gives us the worst case bound, and it may be possible to reduce the burstiness via the multiplexing that we just saw in this example, that the one input was 1 and half constraint, another input was also 1 and half constraint, and if you add them you get an output which is actually 0 1 constraint, which is actually less burstier than what was the what were the two inputs. Okay. So this is one aspect of what happens when these sigma rho traffics gets multiplexed. Now let us consider that this sigma rho traffic is served by a work conserving link, which we have been all through considering, okay, which is basically a buffer which is equipped with a transmitter which transmits at the rate of c per unit of time. All right. So we call this to be a work conserving link. So the server is never idle whenever there is some traffic or whenever there are some bits in the buffer. Okay. So let us define this work conserving link. Now in this work conserving link, what we are saying is that there is a buffer just transmitting at C cells per unit of time. We would like to characterize this work conserving link later on for the rho sigma characterized traffic. Okay, but so what we are saying is right now is AT is the input traffic, where AT denotes the cumulative number of arrivals by the time t. So I want to again re-emphasize this, that cumulative arrival by time t. Okay. For this discussion we may assume that the arrivals occurs at discrete time instant, let us say 0, 1, 2, 3, 4 so on. So the arrival process AT is essentially a staircase function, right. So for this work conserving link, it is easy to see that if Qt denotes the number of packets, okay, in the queue at time t. So if it is number of packets in the queue at time t, okay, so this is essentially a buffer length, okay, then it can be shown that Qt plus 1, okay, is given by Qt plus AT plus 1 minus C plus of this, where this is equal to, where x plus, I am using it to denote, x plus is max of 0 into x. So maximum of this. Now what does it say? It says that the number of packets in the queue at time t plus 1, okay, is equal to max of either 0 or Qt plus AT plus 1 minus C. Now what is AT plus 1? We are saying that AT is given by AT minus AT minus 1. So we are assuming a discrete time arrival process, and AT denotes the cumulative number of arrivals by the time t. So what it is saying is that AT is capital AT minus AT minus 1. So this actually is the number of arrivals. Small at denotes the number of arrivals at time t. Okay. So now what this equation is trying to say is, this equation is trying to say that the queue length at time t plus 1, okay, is given by the queue length at time t plus the number of arrivals that occurs at time t plus 1 minus the number of packets that would have departed at the time t plus 1. Okay. So this was the previous queue length, the queue length at time t. This was the number of arrivals that have occurred at t plus 1. These are the number of arrivals that have departed. So this becomes the new queue length. However, if this is less than c, okay, if this is less than c, then obviously the queue becomes empty at t plus 1 and the queue length at t plus 1 will be 0. So if Qt plus AT plus 1 is greater than c, then this will be equal to Qt plus AT plus 1 minus c, and if Qt plus AT plus 1 is less than c, then the queue length at time t plus 1 will be 0. Okay. So this is a simple interpretation of the fact. I just explained you here because in our next subsequent discussions we would like to consider that there is a Fifo scheduler for the time being, not necessarily a Fifo scheduler but a single buffer. Okay. There is a single buffer equipped with a transmitter which is transmitting at C cells per unit of time, and there is an input arrival process which is AT. We had considered these processes, we had considered these examples earlier also, where we had assumed that this AT was a bursty random traffic and it was being served by a transmitter which was transmitting at C cells per unit of time, and we characterized the effective bandwidth of a traffic source, etc. previously. But right now, we want to consider what we should be calling appropriately as deterministic queuing system. Why deterministic? Because the arrival process is actually deterministic, okay, which is a linearly bounded arrival process. Okay, instead of a stochastic process, instead of a random bursty process as an input to this queuing system, it is a deterministic arrival process, or rather deterministically bounded arrival process, and such a queuing system we would like to characterize. So now we prove a very important result for this work conserving link which is transmitting at C packets or C bits per unit of time. Okay, and that important result I would just like to prove is, let's say that I call it to be another claim is, let's say that Q0 is 0, and let us say that these B, okay, which is Bt for t equal to 0, 1, 2, let's say that this denotes the output from this work conserving link. Okay, so here was our work conserving link, here was the input AT, and let us say that BT is the output, right. Now we want to prove two results. One result is we want to prove that QT is given by maximum over 0 to t, and which is maximized by S AT minus AS minus C into T minus S for all t greater than 0, right. And the other result that we would like to prove is BT, which is for the output, is minimum of 0 to minimum over 0 to t, okay, AS plus C into T minus S, again for all t greater than 0. So we would like to prove this result. Okay, right now we are not assuming the input traffic AT to be a sigma rho constrained traffic, but we will soon assume it to be a sigma rho constrained traffic, and we will specifically see how the Q length, okay, how the Q length and the output departure process behaves for a deterministic queuing system. Okay, so that is what we would like to characterize, how the Q length evolves, okay, and how the output departure process evolves. Note that asymptotic results for a random arrival process for such a queuing system we had considered, and where we had seen that the packet loss rate basically behaves or decays exponentially, and that is how we characterize the effective bandwidths of a random traffic source. Now we would like to consider the deterministically bounded arrival process, and we would like to characterize various queuing parameters, which is like the Q length and which is like the output departure process. Okay, how do they behave? But first consider general result where we have shown that QT and BT we would like to characterize. So we would like to prove these two results. So let us first prove the result which is the first result, and this first result is we would like to prove that QT is given by max of from 0 to t AT minus AS minus C into T minus S. This result we would like to prove. So we prove this result by induction. Okay, so let us prove this by induction. Okay, so let us see what happens for t is equal to 1. For t equal to 1, this result is trivially true, okay, because we know that Q1, which is from the Lindley's equations, is given by max of 0 Q0, which was a Q length at time 0, plus A1, number of arrivals at 1, minus C, that is the number of departures that have occurred. Now note that this is 0, okay, so therefore Q0 is 0, so this is 0 A1 minus C, alright, and this is nothing but we can say that this is maximizing over 0 to 1 over an interval of 0 to 1 and A1 minus AS minus C into 1 minus S. So this result is trivially true for t equal to 1. Now let us assume that this result is true for t, and then we will prove that this result will also be true for t plus 1. So this is we would have proved this by induction. So let us assume that this result is true for t. Okay. So if this result is true for t, then we know that we can write qt plus 1 again from Lindley's equations. It will be given by max of 0 qt plus at plus 1 minus c. Now, since this result is true for t, then we can write this to be max of 0 into maximum over 0 to t given by at minus as minus c t minus s plus this term at plus 1 minus c. Now, this I can write to be max of 0. Note that this maximization is over 0 to t, so I can take this at plus 1 inside, and if I take at plus 1 inside, then this becomes 0 to s, and similarly I can take c also inside because this is independent of s, so this will not affect our maximizations. So, if I take that inside, then this will be at plus 1 minus as minus c into t plus 1 minus s, and this again I can write this to be t plus 1 at plus 1 minus as minus c into t plus 1 minus as. So, this proves the result. So, this we have proved the result that if you assume that the Q length evolution result holds for t, we have proved that it will also be valid for t plus 1. Okay. So, among this we have proved the first claim, that is for the deterministic queuing system, if at is the input and bt is the departures, that is where at denotes the cumulative number of arrivals by the time t and bt denotes the cumulative number of arrivals by the time t, then the queue length will evolve as at minus as, where at is the number of arrivals by the time t and as is the number of arrivals by the time s, and at minus as therefore denotes the number of arrivals during the interval t to s minus ct minus s. We maximize it over the interval 0 to t. Now, let us prove about the bt. Okay, we try to prove this result about bt, and so we try to prove the claim 2, which is not that the departures by the time t is given by the q length which was at time 0, okay, the initial q length, plus at, that is the number of arrivals by the time t, minus qt, which is the q length at time instant t, right. So, this was the q length at time t, these many number of arrivals have occurred by the time t, and this was the initial q length. So, obviously bt will be equal to the number of departures that have occurred. Now, since q0 we have assumed it to be 0, this we can also write to be equal to at minus qt, right. And we have already proved this result for qt, we have already proved this result for qt. So, I will write this result for qt here, and then I can say that this is also given by at minus max over 0 to t at minus as minus c into t minus s. Now, note that this is at and this is at here, alright. So, this will, I can take it inside and this gets cancelled out, but there is a minus sign here. So, therefore, this is equivalent to saying that we are minimizing it over 0 to s plus t as plus c t minus s. So, because I take this minus sign out, okay, and this would be equivalent to then minimizing over this 0 to capital 0 to capital, oh sorry, 0 to t. Okay, so this way we have proved that how the queue length evolves of a deterministic queuing system, which has this input arrival process AT, which is deterministic, discrete time we are assuming for this specific case. Okay, discrete time arrival process, and the number of departures which is BT, where BT denotes the cumulative number of departures by the time t, again discrete time, and we have proved how the number of departures behave and how the queue length evolves, right. Now let us consider the specific cases where this AT happens to be a sigma rho constrained traffic, and then we would try to characterize this deterministic queuing system for a sigma rho constrained traffic. Okay, so let us see for the case when the traffic is rho sigma constrained. Okay, so we would like to see what happens when the traffic is rho sigma constrained traffic. Okay, so I should say here characterization: deterministic queuing system with sigma rho constrained traffic. Okay, so two things we want to prove here. One is, so what we are saying essentially is that there is a buffer which is serving at the rate of C. Input is now sigma rho constrained traffic, and we would like to know two things. One is we would like to know is what is the maximum queue length. Okay, and the other thing that we would like to know is what is the maximum delay. And queue length. Okay, it can be proved. So there are two claims which we would want to prove of such a deterministically deterministic arrival process with rho sigma constrained traffic, which is being served by a work conserving link with the transmitter rate C, and there being a buffer, and we would like to know what is the maximum queue length and what is the maximum delay. So two results we can prove here about the maximum queue length and the delay. One is that so about max queue length, we can prove that if rho is less than or equal to C. That means if the transmitter rate is more than the average arrival rate, is what we are assuming, because the input has an arrival process which is sigma rho constrained. So sigma is the maximum burst size and rho is the average arrival rate. So what we are saying is if the input average arrival rate rho is less than or equal to the transmitter rate, that means the transmitter has a arrival rate more than the transmitter has the output link rate more than the average arrival rate, then we can prove that the maximum queue length of this queuing system will be bounded by the sigma, that is the maximum burst size. Okay, so we can prove that the maximum queue length will be less than or equal to sigma, where Q I am saying is to be max queue length. So this is one important result. The second important result, we would like to know about the maximum delay, and maximum delay is this. For this we need to invoke the assumption that if rho is less than C, then the maximum delay D will be less than or equal to sigma upon C minus rho. Okay, where so this D is my maximum delay. Note that in this in finding out the maximum delay, we are not assuming that this work conserving link is necessarily a FIFO scheduler. We are assuming that it could be scheduling the packets in some other order also, maybe last come first serve also, okay, or some other scheduling order also, but the only assumptions that we are making is that the disk link is work conserving. The scheduler is never idle if there is a traffic in the queue, or if there is a packet in the queue. Okay, the scheduler is never idle, so therefore it is a work conserving link. We can improve this result if we further put a restriction on the scheduler that it is a first in first out scheduler, a FIFO scheduler, or a first come first serve schedulers. Okay, so we will see that result also, but for the time being we assume that we are not imposing any restriction on the scheduler as long as we know that it is a work conserving scheduler. So let us prove the result of the maximum queue length. Okay, all right. So to prove this result, so what is the claim? The first claim was that this queue length is bounded by sigma if C is greater than or equal to rho. Okay, so the proof is since the traffic is rho sigma constrained, AT minus AS is clearly given by sigma plus rho into T minus S, right, for all. Now we had proved for the deterministic queuing system that the queue length Qt evolves as max of, okay, we had already proved that it evolves as the max of AT minus AS minus C T minus S, right. This is what the result earlier that we had proved. So if this result is true, now note that AT minus AS in our case is a rho sigma constrained traffic, so therefore we can write that this is equal to max of right, and which is therefore should be this expression is therefore equal to sigma plus right. Now but rho is less than or equal to C, and therefore we can say that the queue length Qt will always be less than or equal to sigma. Okay, so therefore we can say that the Qt, okay, now since rho is less than or equal to C, it proves that Qt is less than or equal to sigma. So that means max queue length will be equal to sigma, right. So this is what we have proved from this result. Okay, so since rho is less than or equal to C, your Qt will be less than or equal to C. So what we have proved is that if you have a deterministic queuing system where the input is a sigma rho constrained traffic and it is being served by a work conserving link which is transmitting at the rate of C, and this transmitter rate we are assuming it to be greater than or equal to the average arrival rate of this deterministically bounded process, then we can prove that the maximum queue length, okay, will never be more than sigma. So this also gives you an idea of buffer dimensioning in an internet router, okay, that how much we should keep the size of the buffer if we have actually shaped or regulated the traffic by some kind of a rho sigma regulated traffic. Okay. Now let's prove about the maximum delay. Okay. Now we had shown that the maximum delay will be given by this result, right. The maximum delay is, if rho is less than c, then the maximum delay is less than or equal to sigma upon c minus p. So let's try to prove this result now. Now I define the busy period. So we want to prove here the result for the maximum delay. That if rho is sort of less than c, then we want to prove that the delay d is less than or equal to sigma upon c minus rho. Now let us say define the busy period. To prove this result, we define the busy period from t1 to t2. So we are saying that the busy period begins at t1, okay, and at t2 the busy period ends. Right. Now the busy period begins at t1, that means qt1 was actually 0, that a q length at time t1 was actually 0, okay, and at, the number of arrivals were greater than 0, and busy period ends at t2, okay, because qt2 also becomes equal to 0, and during t1 to t2 qt is greater than 0. Okay, so this is the definition of the busy period of this deterministic queuing system, which is being served by a rho sigma constrained traffic and which is being transmitted by a scheduler which is transmitting at c per unit of time. Alright. So now the busy period begins at t1 and it ends at t2. At t1 the queue length is 0, at t2 also the queue length has become 0. During the interval of t1 to t2 the queue length is greater than 0. So there was a continuous backlog here, and so that backlog, all the backlog has been served at t2. So that means by the time t2 all the traffic that arrived during the interval of t1 to t2 has been served. So obviously the maximum delay that a traffic source or a packet will encounter will also be bounded by the maximum length of this busy period. Okay. So if we can determine what is the maximum length of the busy period, we would also have proved what is the maximum delay that a packet would encounter, right. So let's prove what is the maximum delay. Let t, capital T, be the length of this busy period. Okay. So let capital T be this length of the busy period. Then all we need to show is that the capital T is less than or equal to sigma upon c minus p. Now note that the number of packets arrived during the interval t1 to t2, that is a t2 minus a t1, is definitely less than or equal to sigma plus rho into t2 minus t1, which is equal to sigma plus rho capital. What is the number of packets which are transmitted? Number of packets which are transmitted during the interval is c into capital T. So obviously c into capital T is equal to a t2 minus a t1, which is less than or equal to rho t plus sigma, and this gives that t is less than or equal to sigma upon c minus p. Of course, if we are assuming a discrete time arrival processes where the t has to be integer, then we need to take the integer part of sigma upon c minus rho. Okay. So that's what we have proved here, that the delay of a packet in a deterministic queuing system will be bounded by sigma upon c minus rho, where the transmitter's average rate of serving the transmitter's rate of serving is more than the average arrival rate of the input traffic. Okay. So, in that case we have shown that the queue length is also bounded, the delay is also bounded. That means what we are gravitating towards the fact that if we shape this input traffic, or if we regulate this input traffic by this rho sigma characterization, that is a token bucket regulator, then downstream network nodes will be able to offer certain quality of service guarantees, because in that case the maximum queue length and the maximum delay can be bounded, right. Now we will improve further this result by showing that if we assume that this scheduler is actually a Fifo scheduler, okay, not necessarily a last come first serves or any other schedulers, then we can also show that this maximum delay bound can be improved further. Okay. So, what is that result? Okay. For the Fifo scheduler, right, we can show that if, in this case, if the service policy is Fifo, that is first in first out, and then rho is less than or equal to C. Okay. Now, in this case the rho being strictly less than C is not required, rho can be less than or equal, then maximum delay will be less than or equal to sigma upon C. This is because the maximum queue length happens to be sigma, and the packets are being served in the first in first out manner. So, obviously the delay can never be more than the maximum queue length divided by the output link rate of this work conserving scheduler, which is given by C. Okay. So, this is a result if the scheduling policy happens to be a first come first serve. Okay. Now, we will, so we have, so if the input traffic happens to be a rho sigma characterized traffic, then first of all we have shown that what is the effect of multiplexing on these input traffic, which is rho sigma traffic. So, that one part we have seen. The other part then we have seen what is the effect of if this traffic is served by a work conserving link, then what can we say about the maximum queue length and the maximum delay, that also we have seen. Now, we would like to see that when such an input traffic is served by a work conserving link with a transmitter, then what can we say about the output burstiness. Okay. Whether the output is more burstier, and if it is more burstier, then by what amount it is burstier, whether we can reduce the effects of the burstiness and so on. So, that is also we would like to see. Okay. So, now let us characterize the output burstiness of such a work conserving link whose input is a rho sigma constrained traffic, right. So, now we would like to now characterize the output burstiness. Now, some definition are required. Let us say A is the input and B is the output. So, we say that a network satisfies the flow constraint if Bt is less than or equal to At for all t. So, this is our definition. Now, we will prove two results. Okay. So, claim 1, we would like to prove that if the node, the network node, guarantees bounded queue length q, if the network node guarantees the bounded queue length q, then the output B is sigma plus q into row constraint, right. So what we are saying is, if the node can guarantee the bounded queue length q, note that the node can guarantee the bounded queue length, okay, if it's a work conserving link and the input happens to be a row sigma constrained traffic. We have already seen that a node indeed can guarantee the bounded queue length. Then what we are trying to see, that the output of such a node, okay, will also be a deterministically bounded arrival process, but there the sigma, okay, will be sigma plus q and rho. The second result that we would like to prove is that a second conjecture is that, the second result is that if the node satisfies the flow constraint, okay, and guarantees, if the node satisfies the flow constraint, and guarantees the bounded delay of D, then the output B is sigma plus rho D into sigma constraint. And the third result is, we would like to treat is that if the node, the network node is work conserving, then B is also sigma rho traffic. Okay. So what we are trying to say is that if the network node can give us the bounded delay and the bounded queue length, then we can completely characterize the output burstiness of the traffic. Okay. So what we have essentially seen today is that if we have a rho sigma constrained traffic, then what is the effect of the multiplexing, what is the effect on the output burstiness, and what are the effect on the maximum queue length and the maximum delay.